Okay guys, Professor Hildebrandt here. So I'm going to go through a lecture for Chapter 7. So Chapter 7 is going off of what we just did in Chapter 6. So in Chapter 6, we were looking at a probability distribution for discrete random variables, where discrete random variables are the result of counting. So I can count how many students are sitting in a class. This chapter is going to look at continuous probability distribution. So now our random variables are called continuous. Those are the results of measuring something, measuring rainfall, measuring the flight time between two cities. So we're going to start with the uniform distribution. Oh, and we're only going to do the first three learning objectives, 1, 2, and 3. We will not do learning objective 7, 4 on exponential probability distributions. So this is the simplest distribution type for a continuous random variable. It's called the uniform distribution. It's got several characteristics that make it unique. It's rectangular in its shape. Its mean and median are the same. And we say that it's completely described by its minimum value, which we will designate with an A, and its maximum value, which we will designate with a B. Perhaps as an example, we want to look at the distribution of the wait time for an elevator. When we press the button, how long are we going to wait? And so maybe if the elevator is sitting right there on our floor, then we wait 0 seconds. So that's our minimum. And then if it's 2 floors up, there's only 3 floors in the building. Let's say if it's 2 floors up, then the maximum time that we're going to have to wait is 40 seconds for that elevator to come to us. Okay. And so this is what it looks like again. So you can see the rectangle goes from the min to the max, A to B. We also can describe the height. Notice the height, since it is a rectangle, is constant. And our height is represented by 1 over max minus min, or B minus A. And so this is going to be important because we're going to see in a minute that we can find the area of a rectangle by multiplying its height times its base. And so this will simply be 1 over B minus A times the base of B minus A. Okay? So that's where we're going with this. We can find a lot of different things for our uniform distribution. The mean is represented by this formula, 7, 1, just the min plus the max divided by 2. That gives us the expected value for the probability distribution. This is your formula for the standard deviation, okay? So it's the square root of the difference of your max and your min squared divided by 12. And then again, this last equation down here describes the region from A to B. And we can find different, I described it the other day, as we can find different rectangles within the uniform distribution rectangle. And so I'll show you that in a second, and we'll kind of go off of this last formula down here. So here's our first example. So Southwest Arizona State has a bus service, and we want to know how long perhaps we're going to have to wait, okay? Well, if the bus is there when you arrive, then your wait would be 0 minutes. So that's our minimum, or our A value. So here's your A. And the maximum time that our students would have to wait if they just missed the bus would be 30 minutes. Again, for our height, you see here it says 0.0333, and that is because it's 1 over B minus A. So we have 1 over 30 minus 0, or 1/30, which is equal to 0.0333, and so on. So that's the height of it. Well, so what can we do with that? Well, we can take it and we can find the area. And if you're ever trying to find the area of the full uniform distribution, it will always be a value of 1. So this whole orange rectangle here, this whole area has a value of 1, which is what we've talked about already with these probabilities. If we add all of the different probabilities up, we should get to a value of 1. Our mean here is, again, A plus B over 2, so 30 plus 0 divided by 2. And so our expected wait time is 15 minutes. And then the standard deviation is 8.6. So plus or minus 8.6 is the spread that measures the variation in the student wait times. But we can do more interesting things with this. Maybe we want to know the probability that a student will wait more than 25 minutes. And so again, the 0 to 30, this is our full rectangle, right? But we just want to find this orange rectangle within a rectangle right here. I'm going to label it as X1. Okay, so that's what we want to find. Well, so we're trying to find the area between 25 and 30. So our base now is 30 minus 25. Remember, our height has not changed. So our height is still 1 over max minus min times this new base of 30 minus 25. And so you can see they did the work for us up here. And so the probability that the student would wait between 25 and 30 minutes is 0.1667, or about a 16.67% chance. We could also find a rectangle that's kind of in the middle of my uniform distribution. So now my base is from the 20 to the 10. So again, my height hasn't changed, 30 minus 0 times this new base of 20 minus 10, and we would get an answer of 0.333. So a 33% chance that the student is waiting between 10 and 20 minutes. Okay, so let me, oh, sorry, y'all. Let me try to get out of here. Okay, it's not being happy with me. Let me go in really quickly and just add, insert. Oh, it's not gonna let me insert a new slide. Okay, that's fine. I forgot where I put that other app. Let's see if I can do it in this one. So sorry, y'all. I should have had this ready. Okay, so I'm going to work a second example here. We're going back to that elevator. And so again, our minimum wait time is 0 seconds. And then our maximum wait time is 40 seconds. And so if I draw my uniform distribution, A is here, 0, B is here, 40, okay? And I can do several things. I can find my mean, so it's just the 40 plus 0 over 2, or 20. I could find my standard deviation, and so again, the square root of the max minus the min squared divided by 12, and if you worked that out, you would get, I think it's 11.5 seconds, 0.55, okay? And then we could look at some different probabilities. So maybe we want to find the probability that our wait time is greater than 30 seconds. And so we will be looking for the probability of this purple area. So I'm looking for the probability that my wait time, I'm just going to call it X1, is between 30 seconds and 40 seconds. And so again, I do my base times my height always being 1 over B minus A. So my height is 1 over 40 minus 0 times this base of 30 to 40. So 40 minus 30, and we would have 10 over 40, or 1/4, or we call it 0.25, okay? So I could do it that way. I could look for the probability that I'm between 0 and 10 seconds in my wait. So this red area, so the probability that I'm going somewhere between 0 and 10 seconds to wait. So again, 1/40 times 10 minus 0, we get the same thing, 10 over 40, or 0.25 for my wait time. Okay, let's get back in here. So that's the first one. Now we're going to move on to what we call the normal probability distribution. And this one is more complicated. It actually has a fairly complex formula that you do not need to know, but let me just show you. So to find a probability for the normal probability distribution using the formula, it would be 1 over, don't write this down, y'all, the standard deviation times the square root of 2 times pi raised to the e log minus, right? The x value minus its mean squared, squared divided by 2 times the standard deviation squared. We will not use this. Do not use. Okay. Instead, we are going to take our normal probability distribution, convert it to what we call the standard normal, and then there's going to be a chart that's in your textbook, and that's what we're going to use. So here's some things about the normal probability distribution. It's a continuous distribution. It's bell-shaped, so it looks like this, where its mean is right here in the middle, okay? It's symmetrical, so everything on the right-hand side that I just shaded in is equal to everything over here on the left. It's asymptotic, and so what this means is the curve approaches but never touches the x-axis. So it gets closer and closer and closer, but it has tails on both ends. We say that it's completely described by its mean and its standard deviation, and then there's a family of normal probability distributions. I'll show you that in a second. So again, this is what it looks like. So it's got those 2 tails. Again, it's symmetrical. And remember, everything, so the area under the curve is all the probabilities. So that's always going to equal 1. So what does that mean? Well, then it means that the area on the right is equal to 0.5, and the area on the left of the mean, median, and mode is also 0.5. Again, your mean is right here, but your median and mode are all equal, okay? And we call these guys here on the end your tails. So that's the normal curve. Here's our family of normal probability distributions. So we could have distributions where the means are equal, but the standard deviations are different. And so remember, your standard deviation is the spread in our data, or in this case, our probability. And so if the standard deviation is smaller, like this one here, then it is more centered around the mean. So your curve will be steeper, but tighter pulled in. And then as the standard deviation increases, you see that curve start to flatten out. Our second example, we have different means, but the same standard deviation. Different means and different standard deviation. So everything looks different, right? The curves are different shapes, the curves are different heights. But then the last one, we have different means, but we have the same standard deviation. So you can see the height of these curves is the same, the shape of the curves is the same, but they're each centered around a unique expected value. So now we're going to get to what I call the standard normal probability distribution. And this is a specific normal distribution. And it's got some unique characteristics in that its mean is 0 and its standard deviation is 1. And what it's going to do, again, we're going to convert our other normal probability distributions into a standard so that we can have what we call a z-score or a z-value. And so this is a very important formula. Make sure you guys write this one down. To find our z-score, we take the value that we're looking at minus the probability's mean divided by its standard deviation. And so I'll show you what we're going to do with that. So here's a portion of what's called the z-table. Let me just show y'all really quickly what it looks like. I had it pulled up a second ago. Business stats. Here we go. So this is in your textbook. It's the chapters refer it to as Appendix B3. So this is our z-scores for areas under the normal curve. So if you use that formula, right, that I just showed you, it's not gonna let me write on this. So if you use that formula, z equals x minus mean divided by standard deviation, and you get an answer of 1.96, then you use this chart to find the area under the curve that corresponds to a z-value of 1.96. And so to do that, you first go down this first column where you see your z's to 1.9. And when you get there, you go all the way over until you get to 0.6. And you should see the answer there is 0.475. So that's the area under the curve for that z. Okay, so going back to ours, maybe it's we get a z of 1.5. And so we go to our chart, we go again down that first column, we stop at 1.5, and then we go across the row until we get 0.0, and we would find the area to be 0.4332. This one was looking at the grams, so it's like, what's the probability that something will weigh between the expected value and 28.54 grams, and the probability then would be about 43%. So let's work an example so that we can make this make more sense, hopefully. And so this is just talking about Uber. I'm not going to read all of that, so y'all, you can read it. We find that the mean income for an Uber driver is $1,000 a week with a standard deviation of 100. So you'll need those numbers, write them down. So our mean weekly income is 1,000 and our standard deviation is 100. So we could ask questions like, what's the z-value of income for a driver who earns $1,100? So again, I'm going to use the formula z equals x, that would be the 1,100, minus the mean over the standard deviation, right? And so they've written it right there for us. So 1,100 minus 1,000 divided by 100 gives us a z-score of 1. And if we then did it for 900, we would get a z-score of -1. So with chart B3, you only have positive z-values. So if you get a negative, then you use the same number. So you would just look at 1.0 and find the area. But a negative z-score indicates that area is to the left of our mean, okay? And so if we looked at a z-score of 1, you would find the area under the curve to the right or the left is 0.3413. So this brings us to our empirical rule, which I kind of skipped over in chapter 3. But the empirical rule basically says that almost all of our data, so 99.7%, is within 3 standard deviations of our mean. And I can prove this because, again, we just did a z of 1, right? And we found the area to be 3413. So if we multiply that times 2, because, again, it's on the right, but it's also on the left, then we would find that 68% of our data is represented within that first standard deviation. If we then if we go out to the second, so with a z of 2, this is where your z is 2. So you're going, and here's an important thing to remember with these z values. Your z value is always referencing the area back to the mean. So this area is from the mean of 0 over to a z of 2. So it's really, now this is included in it. We would get an area of 0.4772. And again, we double it to get this side as well. And it would be, sorry y'all, 95%. And then if we went all the way out to 3 standard deviations or a z of 3, so now we're adding these little areas in here, we've now covered 99.7%. So that's where the empirical rule comes from. Here's an example of the empirical rule. So we've looked at these batteries. We have a mean life of 19 hours with a standard deviation of 1.2. So we get asked the questions, okay, well, about 68% of our batteries are going to fail between what 2 values? Because it specifically says 60%, 68%. I know that I'm going plus or minus 1 standard deviation. So it's simply 19 plus 1.2 for 20.2 and 19 minus 1.2 for 17.8. If I want 95%, I'll go with 2 standard deviations. So now I multiply my standard deviation of 1.2 times 2, and I would get 16.6 and 21.4 hours. And then virtually all are going to fail within 3 standard deviations. So now I'll multiply by 3 to get 15.4 and 22.6. All right, so back to our Uber example. Recall that with our Uber example, we found the mean income to be 1,000 and the standard deviation is 100, okay? And so we can use this to find different things. And so maybe we're looking at, okay, well, what's the likelihood of selecting a driver with a weekly income between the average of 1,000 and 1,100? So we did this earlier, but my first step is I'm going to calculate that Z value for an X of 1,100, and we find the Z to be 1. Then I'm going to pull up my Appendix B3, my Z chart. I'm going to go down the row till I get to 1 and go down the column and then over the row until I get to 0.0. And my area under the curve is 0.3413. And so again, that represents the area from the mean up to my X value of 1,100, or this purple shaded region here, 0.3413. So that's the first question I answered, okay? So what's the likelihood that the income was between 1,000 and 1,100? But maybe I want to look at a second question that's just, well, what's the probability of selecting a driver who earns less than that X value of 1,100? So yes, this 3.43, this purple region, is less than 1,100, but so is everything to the left of my mean. And so remember, our curve is symmetrical, it's cut in half, and our total area is 1. So the area on the left-hand side of the mean is 0.5. So we take the 3,413, the purple region, we add it to the 0.5 left region, and there's an 84% chance that the randomly selected Uber driver earns less than $1,100 a week. All right, I also, though, can find, I just have to do a little bit more work, but I can find the probability in one of my tails. So I want to know the value or the probability that my driver earns less than 790. So to do that, though, my first step is to find the probability that the income is between 790 and 1,000. Why? Because my Z's are always referencing me back to the mean. So I find that Z, so I've plugged in here, find my Z to be negative 2.1. So again, I'm going to look for a positive 2, so I go down my column of Z's until I get to 2.1, and then I'm going to go over in my row until I get to 0.0, and the area is 0.4821. So that's this kind of orange area. That's the probability that the income of the driver we select would be between 790 and 1,000. But maybe the question I really want to answer is, what's the probability that the driver randomly selected has income less than 790? So that's what I meant when I said the tail down here. Well, again, you have to find first the 790 back to the mean of 1,000. And because then I know that everything left of the mean, that whole area, equals 0.5, if I want to find this little bitty gray tail down here, this area right here, then I take 0.5 and I subtract the area of 0.4821 to get the area in my tail of 0.0179, or only about a 1.79% chance that that driver that we randomly select has an income less than 790. Not bad at all for just driving people around, huh? I can also find the area on both sides of the mean. So now we're looking at the probability from different sides of our mean. And so it's going to be a two-step process. You're going to calculate your Z-score on the left-hand side. You're going to calculate your Z-score on the right. And then we're going to add them together. So step 1, I find the income for a driver who earns 840. And so again, I'm comparing this back to my mean of 1,000. And so we put it in, we get a Z of negative 1.6. I use my B3 appendix and I find this area to be 0.4452. And then I go, okay, well then what is this area from 1,000 up to 1,200? And I find a Z of 2. Again, I look at my Z chart and I get an area of 0.4772. And now this time I add them together. And so we have about a 92% chance that our randomly selected Uber driver has an income between $840 and $1,200. So that's the question we were answering. So income between $840 and $1,200. Okay. We could also look for a probability in between two numbers that aren't the mean, but they're on the same side of the mean. So now we're looking at the same side of my mean. And for this one, I'm looking for an income between 1,150 and 1,250. And so we're going to try to find that probability. Again, we have to do the individual z's first. So I first do an x of 1250, step one, and I would find a z of 2.5. I would look at my chart, and my chart, again, is going all the way back to the mean. And so it's the area from here all the way up here to 1250, and we find from our z chart that that is equal to 0.4938. Then in step two, I find the z for 1,150, and it's 1.5. I look at the chart, and so this is from here to here, and it's 0.4332. But we want just this purple region, right? We want the probability that they're between 1150 and 1250. So we take the 0.4938 and we subtract the 0.4332 for a 0.0606, or about a 6% chance that our randomly selected Uber driver has income between 1150 and 1250. Okay, so this is the last thing I'm going to do in chapter 7. I'm still working off of those standard normal distributions, and I'm still going to use my z formula, but I am going to use it in a different way. So recall, my formula is x minus the mean divided by the standard deviation. So you've got this tire company, and they've already figured out a few things. They know that their mean mileage for their tires is 67,900 miles. So the tires are expected to last on average 67,900 miles, with a standard deviation, though, of 2,050 miles. We find that the distribution follows the normal distribution. So we've got the bell-shaped curve with our centered around our mean. But what we're looking for this time, we're not looking for, okay, here's my x value. Now go find the area under the curve. Instead, we're saying this is what we're comfortable with being. This is the probability area we want to be in under the curve. What is the corresponding x value? So we're going to reverse order work through this. So very specifically, they want to make a guarantee on a minimum mileage that these tires are going to last, but they don't want to have to replace any more than 4% of the tires. So they want a failure to meet the average rate of less than 4%. So again, here's my mean of 67,900. So where is that 4% under the curve? Well, it's going to be to the left of the mean, because it was miles that we didn't, tires that didn't make it as many miles as we wanted them to. And so this little tail over here, this kind of, I'm going to color it in this red region, that's 4% or 0.04. So now I need to find the z value that corresponds to this so that I can find the x value in terms of the number of tires for my minimum mileage guarantee. Remember, though, that our z's take us back to the mean, so we need to know the value from this point back here. Well, again, everything to the left of my mean is 0.5. So 0.5 minus 0.04 gives me an area under the curve of 0.46. So now I'm going to go, so that's what we figured out, that area. Now we go over to the appendix B3, looking at our z-scores. And again, we don't know the z. We're trying to find the z. We know the area that we want is 0.46. You won't find it. There is not a 0.4600 on the chart. However, the closest we have is an area of 0.4599, which corresponds to a z of 1.75. So my z equals 1.75. So now I know three of my unknowns. I know my mean, I know my standard deviation, I know my z. I will use those to solve for my x value. And so that's what we've done down here. Z equals x minus 67,900 divided by 2,050. And we found our z again, it was negative 1.75 because it's to the left of the mean. We plug in that negative 175, we cross multiply, we solve for x, and this would be our final answer. So we would do a guarantee, these tires, they're gonna last at least 64,312 miles, and we shouldn't have to replace any more than 4%, which was the company's goal. So that's another way that we can use our normal distributions in a practical way. I hope this helps. You guys let me know if you have any questions.